Okay. Good afternoon, everyone. Hopefully, everyone's doing well. We are going to get started with today. Today is sort of we're going to be covering work again, but today I'm sort of envisioning it's going to be the last day. We're going to keep working on work in class. So first off, let's first start off with a warm-up question. This warm-up question is going to be targeting finding the work when there is kinetic energy involved. So here in this problem, I'm throwing a 5 kilogram ball at 4 meters per second. So in this problem, I have a 5 kilogram bowling ball. It's initially at rest, which means it's initially not moving. And then I throw the 5 kilogram bowling ball at 4 meters per second. So our goal here is to figure out how much work it takes to throw a 5 kilogram bowling ball at 4 meters per second. So to do this, what I recommend is first, A, figuring out the initial kinetic energy of the bowling ball. B, finding the final kinetic energy of the bowling ball. C, is the bowling ball going up or down? And then D, finding the work. So we'll take a few minutes to see if we can figure this out. See if we figure out this warm-up problem. I think the best place to start is to figure out what the initial kinetic energy is. Then you can figure out the final kinetic energy is. Answer is the bowling ball going up or down. The reason why you want to answer is it going up or down because that helps you find if the potential energy is changing at all. And then last but not least, find the work.
Mr. Hu?
Yes.
I know that the assignment yesterday was to do the work proficiency assignment. But if we do want to do the mastery assignment too, when's the official due date for that one?
There's no official due date for that. It's just that we won't have any more class time after today. So you can keep working on it afterwards, but we just won't be working on it during class anymore.
Got it. Thank you.
Yeah. A few answers so far. We can keep working on this. Take your time with it. How much work does it take to throw a 5 kilogram bowling ball? Usually when you bowl, if you've ever bowled before, you usually throw a bowling ball horizontally, right? You generally don't want to bounce a bowling ball. It'll definitely hurt the floor, if not break your legs. So don't throw a bowling ball to the ground. You throw a bowling ball horizontally. So that's very important. The bowling ball is initially at rest. So I want you to figure out the initial kinetic energy of the bowling ball. Remember, the initial kinetic energy relates to how much energy a bowling ball has. And the beginning, how's the final kinetic energy of the bowling ball? That's basically how much energy, kinetic energy the bowling ball has after it's finished moving, after it's moving. Then we want to figure out, is the bowling ball going up or down? The reason why I'm asking, is the bowling ball going up or down? Is because it basically just tells us, is the bowling ball's potential energy, is that changing at all, right? If it's not going up or down, it's not changing. So that means we don't need to figure out the change in potential energy. And then last but not least, find the work. Thank you for asking how my day's been, Miguel. It's been better. It's been better. But you know, hey, it's all about having a positive attitude. So we're gonna get through this. If you're unsure of, how to do this, see if you can answer any of these questions. So if you're unsure of maybe how to do A or B, see if you can answer C, right? If you can just answer C, put your answer to Z and the C in this Zoom chat, right? Is the bowling ball going up or down? That's a very important question. So feel free to answer that in the Zoom chat as well. Don't be too shy to answer C at the very least. And then we'll see if we can get a few more answers here. We'll take a couple more minutes or so. People continue joining us, and then I'll start working through the problem on the board. Okay, so as we keep working on this, I'm going to start going through this on the board. So first, I think generally a good way I like to start some problems, I like to visualize it by drawing it first. So what I'm first going to do is I'm going to draw my bowling ball. So Mr. Hu is a very bad bowler, and so when I bowl, I usually like to bowl with the really, really, really small weight ones, like the really light ones, like the 6-pound weights. Those are definitely my cup of tea. But in this problem, this bowling ball has a weight of 5 kilograms. And so when you bowl a bowling ball, you ideally you roll it on the floor, right? You're not like throwing it like a baseball. You're not shooting like a basketball. You're not even kicking it like a soccer ball. You're literally just trying to roll it perfectly on the floor. And so because it's always on the floor, the height is always 0 in the beginning. So in the beginning, the rolling ball has no velocity. Right, it's at rest. So V is equal to, what I'm going to say that V is equal to at rest. And then at the end here, it has a velocity of 4 meters per second. So this is how I like to visualize the problem. That way you can sort of see what's going on here. Let's pretend that these bowling balls are touching the floor. Okay. So the first thing we want to do is I think it's a good place to start here is to just figure out, okay, what's the information we're given in the problem? So there's a few things we're given. We're given the mass, and this is 5 kilograms. We're given a velocity. There's important distinction here. There are sort of 2 velocities that are given actually. The first velocity we're given is the final velocity, which is how fast it's moving at the end, which is 4 meters per second. Another thing that we're given is that the initial velocity is at rest. This is given to us, and this is very important. And so because it's at rest, it means that it's initially not moving, right? That's what at rest means. When you're resting, you're not moving. And so when I say something is initially at rest, what I'm just saying is at the initial velocity, at the very beginning, it's not moving. So the initial velocity is actually 0 meters per second. So this is given to us, even though numerically it isn't, right? And that's an important part of reading the problem is being able to say, oh, it says at rest. That means that at that point, it's not moving, which is very, very, very important. Okay, so the main unknown we're looking for is work here. In terms of unknown for you. But we're also in the problem, I've also asked you to figure out your initial kinetic energy and your final kinetic energy. And the main reason why I'm asking you to do these is because these will actually help you find your work. But the main thing we're solving for is our work here. Okay, so in terms of finding the initial kinetic energies, so in terms of finding the kinetic energy, we're going to use the formula here. Kinetic energy is equal to 1/2 mv squared. That's a very good one to use. And then what I'm also going to use the formula for work, which is the work is equal to the change in the kinetic energy. Right, remember, this delta K means change in kinetic energy plus the change in potential energy. Before I start substituting stuff in, I first want to take a look at whether or not the bowling ball is going up or down. So in this problem, the bowling ball is just going horizontally. So because the problem didn't say that the bowling ball was going up or down, up or down, right, the change in the height is, there's no change in height, which means that delta P is 0. This is very important. This is very, 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 very important. A lot of people sort of get to see a problem and they're like, I don't know how to find the change in potential energy because it doesn't say anything about height. Do I need to use my height from a previous problem? And the reality is, if it doesn't say that it's going up or down, you know that the change in potential energy is 0. It's just the potential energy is not changing. It's because the height isn't changing. So that means we already know our change in potential energy here. We already know this is 0. So to figure out our work, all we need to do is we need to figure out our change in kinetic energy. Okay, so right off the bat, when we substitute things, what we're going to do is we're going to substitute our stuff in for kinetic energy. So our initial kinetic energy relates to our initial velocity. So this is 1/2 times mass, which is 5, times v squared. Our initial velocity for initial kinetic energy is 0. Our final kinetic energy is 1/2 times mass times final velocity squared. And then the work is just the difference in this. Okay, so the thing is, what I did here is I mathematically showed you how to figure out your initial kinetic energy. But a faster way of just doing this is to recognize that if you have initial 0 velocity, if you're not moving in the beginning, your initial kinetic energy is just 0. Okay, so then we can figure out our final kinetic energy. So we're going to do is 5 times 4 squared. 4 squared is 16, so this is 1/2 times 5 times 16, and this is 40 joules. It's very easy to forget either the 1/2 or to forget the squared. It's very, very, very easy to forget those. So when you're doing a problem here, make sure that you're just double checking your formula to make sure that you didn't drop a 1/2 or a squared somewhere. Okay, so now we know my initial kinetic energy was 0. We know that my final kinetic energy is 40. So in other words, what just happened is that somehow, somewhere, right, we gained 40 joules of kinetic energy, right? That's what our change in kinetic energy is. Somewhere, somehow, we gained 40 joules of kinetic energy. So in order to gain 40 joules of kinetic energy, the work I did is equal to the change in kinetic energy. So the work I did is equal to the final kinetic energy minus the initial, which is 0. And then what I just said is the work is 40 joules. So so I would say this problem is, it can be a little intimidating. What I would say, I'm going to tell you some tricks of the trade here. Some very important things to take away from this is that generally, if the problem doesn't say one thing, so if it doesn't say that it's speeding up or slowing down, or if it doesn't say it's going up or down, you know that one of the changes is 0. This is very, very, very important. And I want to reiterate this. If it doesn't say that it's going up or down, or if it doesn't say that it's speeding up or slowing down, you know that that particular change in energy is 0. So when you figure out your work, all you have to do is you just have to figure out the change in your other kind of energy. Now, in terms of figuring out the change in energies, what does it mean to find the change in energy? To find the change in energy, you're just comparing the amount of energy you have at 2 particular points in time. So in this example, I was comparing the 2 energies after the bowling ball was moving and before it was moving. And in this example, I had before it was moving, it was traveling, it was at rest. Very important. At rest means it is not moving. So if it's at rest in the beginning, it has 0 kinetic energy because it has 0 velocity. And then and it has 4 meters per second of velocity at the end, which means that we can figure out the final kinetic energy using our kinetic energy formula. Does anyone have any questions about this? Did I go to UCLA? I did go to UCLA. I do. Yes, I have a lot of UCLA stuff. But yes, I did. If you don't have any other questions, I'm going to let you keep working on work stuff. So here's our agenda today. Just finish the warm-up. I want you to work on the work proficiency assignment. If you finish with that, you can do the work mastery. Due dates. So I want you to finish work proficiency by next Monday/Tuesday. I asked you to submit it today, by today, in terms of your incomplete stuff. I want you to finish it by next Monday/Tuesday, because we will be starting the last topic in energy power next Monday. So you can turn in work stuff afterwards. That is okay, but we won't have. Yes. So you can turn in any work stuff afterwards, like the mastery or the proficiency. You can turn in afterwards, but we won't have any more class time to work on work. So I would recommend you finish it over the weekend, so that way you can stay on top of things for next week. But if you still can't finish it this weekend, that is okay. You can turn it in afterwards. We just won't have any more class time to work on it. So I recommend you use this time wisely, and make sure you ask questions if you have any. If I gave you some practice problems to work on, I would recommend you submit those. Those will also be helpful in submitting those, and I can take a look at those as well. Otherwise, I'm going to let you get started, and please let me know if you have questions, especially now. If you have any questions right now, so send a message to me right now, and I can answer your question first before I make the rounds and see how everyone's doing. So if you have a question right now, message me right now, and then I will go and answer your question before I see how everyone else is doing. So we have a minute left in class, so I'm gonna wrap up. So, for the weekend, I want you to try to finish, well, I want you to finish work proficiency by next Monday, because you'll be starting the last topic power next week. So I want you to finish by next Monday and submit it. You can turn in any work stuff, so proficiency or mastery afterwards, but we won't have any more class time to work on it. So because of this, I would recommend you try to finish it over the weekend. If you have any questions on it, please reach out to me. You can email me, message me on Canvas. I also have office hours, which are today from 2:40 to 3:40 and tomorrow at the same time. So I would highly encourage you to stop by and say hi and ask any questions you have. Otherwise, you're free to go, and I will see you all on Monday.
Thank you.
Thank you.
Bye. Bye-bye.
Thanks, Mr. Wu.
Peace.
Peace. Peace.
Mr. Wu,
Yes.
office hours start at 1:30
2:40. 2:40.
at 2:40.
Yes, but I mean, if you want to hang around or come at 1:30, Jojo, I can also do that.
Wait, can you repeat that again?
So they start at 2:40 officially, but if you want to come earlier, I can also open up office hours earlier too.
All right. So I just wanted to work on some assignments, only like 2, really.
Okay. Okay.
Can I do them right now
Yeah.
and ask you for, okay.
Okay. Yeah.
I need help with the roller coaster tycoon part 6. Question 4A.
Okay. So part 6. So the point of 4A is to figure out how much kinetic energy you have after you lost a lot of it because of friction. So first off, the first thing we want to do is we want to start off with filling in how much. Okay, so let's do this visually. So basically what's happening is you have 2 hills, and right around here, we want to figure out how much kinetic energy we actually have after we lost a bunch due to friction. So the first thing we want to do is we want to identify our givens. So we want to identify how much our original kinetic energy is. And then we also have 2 blanks here for what else we know. So first off, Jojo, why don't you tell me how much your original kinetic energy you have at this point?
From my first hill.
Yeah, originally, yeah, the bottom of your first hill.
At the bottom of my first hill, I have 6,420 total kinetic energy.
Okay. What else do we know at this point, Jojo?
That my potential energy is 0 because I'm at the bottom of my hill. And I also
Perfect. It's very smart. There's one other thing we know.
total energy. Oh, percent, right?
Yeah, we know our total energy. And what's our total energy here?
Total energy is 300,020. No, 325,280.
Okay. So total energy is 325. I'm just gonna say this just to make my life a little easier. But I know you get the exact number. Okay. So I'm a little confused right now, Jojo, because your original kinetic energy was 6,000. Your total energy is 300,000. So, and your potential energy is 0. So where did all of the extra energy go?
I'm going off of the potential energy from the top of my first hill, not the bottom of my first hill.
Okay, so let's go at the bottom of your first hill.
Wouldn't it be the same as my kinetic energy?
What would that be?
6,420.
So your total energy is 6,000? So what's the same as your kinetic energy?
My energy, my total energy.
So we know this. What the problem is saying is that this is what we originally had. What the problem is saying is we lose 50% of our kinetic energy due to friction. And that friction converts that into thermal energy. So now we want to figure out how much kinetic energy we have now and how much thermal energy we have now.
So my original kinetic energy is 6,420. I would need to divide by 2, right, in order to get my thermal energy.
Mm-hmm.
And so my thermal energy would be 3,210.
Perfect. And how much kinetic energy do you have now after you lost a bunch due to friction?
The same amount, correct?
So what is that?
3,210. It would be the same as the thermal energy because I lost 50% of it.
Perfect. Okay.
So
So now I just want you to.
It
Now I
says
just
I
want you
need
to.
the velocity too, right?
Yep. So why don't you find your velocity?
Velocity is 24.
And so you found your velocity from your new kinetic energy?
Huh?
You found your velocity from your new kinetic energy?
Yes. No, from my original kinetic energy.
You should find your new velocity from your new kinetic energy.
So I already have my kinetic energy, so 6,420.
Your new kinetic energy.
I would divide by 2, right?
Yep.
Divide by 2. And then I would square root it. $56.6.
What do you say?
How 56.6? Would that be wrong?
That seems because that's bigger than your original one. This one should be smaller.
Yeah, I divided by 2, and then I squared it.
What did you start with?
Huh?
What did you start with as your kinetic energy?
600 and 400. Oh no, wait. No, okay, no, I see. Hold on. I see the problem.
Mhm.
$40. Right?
40? Your velocity is 40?
Yeah, correct.
Okay.
Right.
So let's just double check. So what did you start off with as your kinetic energy?
3,210.
And then what did you do with this?
I squared that. No. 300. No. I did 3,210 divided by 2, and then I got 1,605, and I square rooted that, and I got 40.
Okay. So our kinetic energy is equal to 1/2 mv squared. So to get rid of the 1/2, you can't divide it by 2 because it's already divided by 2. If you want to get rid of this 1/2, what do you have to do instead?
Multiply.
You can't divide it by 2.
Multiply, right?
Yeah, you multiply. So if I multiply this, what I get is 6,420 is equal to m squared. So how do you solve this, Jojo?
I would multiply, right? Multiply. Oh no, you already did that. I would square it.
Square root it.
Uh-huh.
You would square this?
Yes, right. No, I'll
Okay, so
divide by 2.
You divide by 2?
Yeah, right.
Okay, so I divide by 2. Okay, but this just looks like where we started off from.
Mm-hmm. We're not
So we
divide by.
start,
No, I would divide by 2 from 3,210.
okay, so I divide by 2, so I get 1605 is equal to 1/4 mv squared. Is this what you wanted to do?
Yes.
Okay, so how do you want to get rid of this 1/4 then?
I would multiply 1/4, right?
You multiply both sides by 1/4.
Yeah, both sides by 1/4, right?
Because that would give you like 401 is equal to like 1/16 mv squared.
Now I would square it.
Now you would square it. Okay. So now we get like 16,000 is equal to 1/256 times m squared v to the 4th.
You a 0. I think you added a 0.
So 400 squared is 16,000.
Oh, I meant the square root.
Okay, square root. Okay. So this is roughly 20 is roughly 1/4 square root of m times v.
It'll be 20, right? My velocity would be 20.
Okay, so the thing is, you have 20 is equal to, you still have this 1/4 term. Because what happened was I divided 3,210, I divided by 2, because you said because we wanted to divide by 2, and then you square rooted it, and then you divided it by 4 again to get 1/16. I square rooted it, so I got rid of the 400, it's 20, but I still have this 1/4 term. And I also have this weird square root of m term here.
So I'm looking to get rid of the 1/4.
Mm-hmm.
Could I divide it by both sides, 1/4 by 1/4?
Okay, so if I divide those by 1/4, I get 5 is equal to 1/16 times root m times v.
Is there a way I could get over the fractions?
So instead of dividing it, what else could you try?
Multiply?
Okay, multiply. So what do you want to multiply by?
How can I get rid of it by multiplying? What would I multiply by?
What do you think?
1/4?
So when you multiply by a fraction, you make it smaller. So in this case, we actually want to make it bigger. So if you want to get rid of the thing on the bottom here, Giorgio, you can multiply by this number on the top. So if you want to get rid of this 1/16, you just multiply both sides by 16, not 1/16. So if we do that, Giorgio, we get as 80 is equal to the square root of m times v. The thing is, Giorgio, we never got rid of this m term, this mass term. So we still have the square root of m in here. Remember, the m is the mass of your roller coaster.
Wouldn't I just fill that in? I mean,
Yep.
for
Yep.
535, right?
Yeah, so what is the mass of your roller coaster?
535 kilos.
Okay, so 80 is equal to the square root of 535 times v. So why don't you tell me what you get for v?
Can you repeat that again? So
Here's what happened. So I took the mass you gave me, I put it into the square root of m. So now what I have is 80 is equal to the square root of 535 times v. So why don't you try to simplify this and tell me what you get for v?
So 80 is equal. So I'm scoring 535.
Yeah.
23 point 13.
Okay. So what do you want to do with that?
Wouldn't that be my new velocity, right?
So that's the square root of 535.
Mm-hmm.
We still need to figure out our velocity here. So I wrote the square root into here. What do you want to do now?
I could divide 80 by 23.
Perfect. Okay. And tell me what you get.
Three 3.4.
Perfect. Okay. So now we have our velocity, 0.4. Now we just need to work on to the last problem. Figuring out the highest second hill that you can climb.
So my new velocity is 3.4, right?
Mm-hmm. Mm-hmm.
And then now for B, the unknown. What would I put right there?
For you just put in your velocity, right?
Huh?
You just put in your velocity.
For the unknown for B.
Yeah, that's what the velocity is.
There's 3 spaces.
Yeah,
That's
so
not-
your unknown is you're looking for your kinetic energy, your thermal energy, and then your velocity.
Oh, I already found all those. So KE,
Mm-hmm.
TE, and V. And then it says, write the equation to find the new kinetic energy from the old one. So I would do KE prime, right? KE minus KE prime. And prime meaning the new KE. And that'll be the difference, right?
Okay, yeah. We could do it, yeah.
So my old kinetic energy was 6,420, right?
Mm-hmm.
6,420 minus 3,210.
Mm-hmm.
And I just get 3,210.
Yep.
So KE equals 3,210. And then for C equation, and then part 3 of it, the one right before D is energy total. So my energy total is KE plus KE, right? Or is it no KE plus PE?
Yep. Nice.
And then write down your substitutions here. So I already know my new kinetic energy is 3,210,
Yep.
right? And my PE would be 0, right? Because I'm at the bottom of my hill,
Mm-hmm.
right?
Mm-hmm.
T 0. And then I have to find it again, right? We're not just putting the same thing. It says solve. New
Yeah,
case.
yeah. You just put your answers in there.
So it's the same thing from the past one, right?
The pause was just to tell you what you were looking for.
Oh.
Yeah, but you can just put in your answers here. That's fine.
Turn the velocity and slash s. Starting from the bottom of the first hill, what is the highest possible second hill that the roller coaster can climb? This is very tricky because while energy is conversed, the roller coaster itself has less total energy than it did before. You will also want to think about how much potential energy the roller coaster will have at the top of the second hill. So am I finding just the total energy of the roller coaster?
So basically what you're saying, basically what happens is you have a roller coaster at this point. You know a bunch of energies here, you know a bunch of your new energies, and you want to figure out what is the highest hill you can actually climb now that you've lost a bunch of energy due to friction.
So basically, I would want to just test out different heights of a hill, right?
You could test out a bunch of different heights, but there is a way to just figure out what is the highest height you can get.
Okay, well, is there a formula for that? Can you show me the formula?
There are a bunch of formulas you can use, but I want you to think about that. I want you to try to set up this problem first.
How would I set it up?
Okay, so let's see. Why don't we first figure out some various informations we know, and that'll help us with terms of figuring out how high a roller coaster can go. So after we lost energy due to friction, Giorgio, after we lost a bunch of energy due to friction, how much kinetic energy do you have now here? So after you lost friction, how much kinetic energy do you have?
I have 3,210.
Mm-hmm. And so how much energy would your roller coaster have now?
3,210, right?
Mm-hmm. Okay. So we know this is very helpful for us. Now, when we want to get to the highest point here, what else? What do we know about this point? When we reach the maximum height that this roller coaster can go up to, what are some things that we know? Go ahead.
Potential energy would be the same as our kinetic energy.
The same as what kinetic energy?
Our potential energy would be the same as our energy because we would have zero kinetic energy because we would be at the max point of the hill.
Perfect. Okay. So how much numerically would our potential energy be at this point?
So my roller coaster is 535 kilos times the gravitational times, which would be times 10, and then times height, and my second height of my roller coaster. No, wait, I don't know the height because I'm solving for
So in this particular problem, we don't know the height. We're trying to figure out the maximum height you can go up. So from this problem, we know that at this particular point, we know that our kinetic energy is 0 if we want our roller coaster to go up the highest possible. What I want you to figure out is how much potential energy do we have at this particular location after the roller coaster started from here and went up to here. And I don't think you don't need to calculate anything for this. You should be able to just figure it out.
Can you repeat that again? Sorry, it's just a loud outside.
That's okay. So we're trying to figure out the height of this hill. So we don't actually know the height here. We want to figure out the highest hill we can climb. At the highest hill we can climb, as you were saying, we know that our kinetic energy has to be 0 because we want our roller coaster to basically not be moving at the top. So we know that kinetic energy is 0. We know that we start off with this amount of energy. What I want to know is how much potential energy do we have at this maximum height here? How much potential energy do we have? And you don't need to calculate anything.
So how would I find the potential energy when I don't have the height?
There is another way to figure out your potential energy without knowing it.
The velocity?
You wouldn't use your velocity. And here's a better question. How much total energy would you have at that height?
The amount of energy that my potential energy has.
Okay. You're absolutely correct. Where else can you find your total energy from?
From my finding my KE and my PE.
Okay.
Oh
The
wait,
thing is,
go to my old total energy now, which is subtracted by my total kinetic energy now, and now I have my potential energy, right?
okay. So that's exactly how you would find your potential energy here. You would take your total energy and you would subtract your kinetic energy and you would get your potential energy. You're 100% correct. And we know that our kinetic energy is 0. So as you're saying, our total energy is equal to our potential energy. The problem is right now in our board, we don't know our total energy. But we can figure this out without actually having to do any math.
We would just go to our old our original energy.
Okay, so why would this equal our original total energy?
Because energy stays the same throughout the roller coaster.
Perfect. Okay. So how much would our total energy be here then at the top?
32, 10. It'll be 300,020. No, 322,070. 100.
Wait, where did you get 22,000s?
Huh?
Where did you get that number? How did you get that?
I subtracted the total energy, which is 325.
Oh, I see. So you subtracted your total energy from here, which is 320,000. Okay, so now I'm a little confused. So your total energy at the top here was 320,000. Somehow we lost a whole lot of it here. I know that we lost some of it due to friction, but this number is way smaller than this one, which seems a little weird to me. And then now we're back at 320,000 here. So what could have happened here? So first off, Jojo, why was our number for our total energy here so much different than this one?
Oh wait, wouldn't my potential energy would just be? Oh wait, was it off?
Finish your thought first. Whatever thought you had, just finish it first.
So it would be 300 and 2000, right? I mean 3,000 and 2,000, right?
Yep. 3,210. Yeah. So then our potential energy, as you were saying, will be 3,210. And I know you can figure out your height from this, Jojo. I'm very confident in you. So I'm going to let you figure out the height from this. The bigger question, Jojo, the one I was sort of asking is, I know how we did this, and this is all correct, and I like how we did this. I'm more confused as to how we went from this big of a number from energy to a very small one. And I know we lost a lot due to thermal energy, but we shouldn't have lost this much. So where did all this energy go? Or what happened here?
Right.
Sorry?
We lost it to friction.
We lost a lot of it due to friction, but I don't think we should have lost this much.
Maybe
So
calculation.
our original total energy down here before we lost anything due to friction, you said was 6,420. So how did we go from 320,000 to 6,420?
We lost it because our potential energy went out. From at the bottom of the hill, we had 0, and we lost a lot of it due to friction.
Okay, so you're right. A potential energy at the bottom of the hill is 0. Lost a lot of it due to friction. So the thing is, without friction, this total energy and this total energy should match up without friction. The problem is right now, this number is so much bigger than this number without friction. So that, I think, is the bigger question. What happened? Why are these numbers so different?
I don't know. So without friction, maybe my calculations were off, right?
Maybe. So where did you get this 6,000? How did you find your 6,420? What was that? Where did you get that?
I got it from kinetic energy.
This at the top here. Is that what you're saying? The top of kinetic energy here is 6,420?
No, at the bottom. We're going at the bottom of the hill.
Okay. So where did you get this number from? How did you calculate that?
From my height at the bottom of the hill.
Okay, so the height of the bottom hill is 0, so our potential energy is 0. But how did you figure out our kinetic energy though?
Can you repeat that again?
So I know you said we got it from our height, and we know that our height at the bottom of the hill is 0. I'm still curious as to how we figured out our kinetic energy at the bottom.
We got that number from having to find my from having to find the kinetic energy, right?
Okay, so how did you figure out your kinetic energy?
By squaring it.
So you know your velocity down here.
Square root, yeah.
So how did you figure out your velocity down here?
I got my velocity from 3.4.
I'm sorry?
I got my velocity from 3.4.
From 3.4. Oh, okay. So that was after we did our velocity with friction. I'm talking about how did you figure out your original kinetic energy without friction?
Oh, my original kinetic energy from 1/2 times the mass times the velocity.
Okay, so how did you know your velocity down here?
And I know my velocity down here because I'm going off my my initial calculations.
Okay, so how did you do those initial calculations?
So my initial if my new kinetic energy is 6,420, then oh, hold on, Mr. Who. My computer's overheating. Sorry, Mr. Hoop.
It's okay.
So, can you repeat that again? I think I
Okay.
kind of got lost.
So we were sort of trying to figure out where you got your kinetic energy down here initially. And you said something about your initial calculations.
So, if my max is 534, I had to find my velocity. And my velocity at the time was before I did and I just lost everything. Hold on, Michelle. I gotta get back to Google Docs.
Okay, it's fine.